Um, Good morning. It's my great pleasure to give you a presentation today on Parker Solar Probe, which is a mission to touch the sun, or as I like to say, the coolest, hottest mission under the sun. I am Nicky Fox. I have the great privilege of being the project scientist for this awesome mission. So Elsa did a really nice job of teeing up space weather and the importance of the sun on our planet. But oops, which way do I? That one? Okay, what do I press? Okay, next. Great. So, so I want to take you back to 1859, which was the first time that we actually realized that the sun had a profound impact on our planet. And so, you see up here Carrington looking at his, looking through his brass telescope, sketching sunspots as he did every day, because that was what they did for fun back in 1859. He was sketching his sunspots, and he saw two bright flashes of white light appear. And he ran off to get a friend to say, golly, look at this amazing thing. By the time he came back, those bright flashes had disappeared. However, just a few hours later, compass needles at the Earth began to spin, and the telegraph system went down for many days, which probably back then wasn't so bad, but try telling your kids they wouldn't have an iPad for 4 days and watch the terror appear. So this was back in 1859. Over the last 150 plus years, we've made a lot of discoveries about our sun. Next, please. The first discovery, again, using some of the material that Elsa has beautifully shown, here is us looking at the sun in different wavelengths. And these different wavelengths from the images basically they correspond to the distance away from the sun, from the surface. And so we start at a fairly cool 6,000 degrees centigrade, 10,000 degrees Fahrenheit. As we step away from the sun, you notice that now we're up at 3 million degrees. And that just kind of breaks the laws of nature. You shouldn't get hotter as you get away from the heat source, but it does in the sun. So next slide. So our first mystery is, why does the temperature rise as we move away from the surface? This coronal temperature inversion, we really don't understand. The other thing we've done with the next slide, please, is with these amazing, this is a nice coronagraph image, we can now image what this solar wind looks like. So as Elsa said, we used comets to be able to tell us that there was a continual stream of plasma coming from the sun. And we know it's extremely, extremely dynamic. But once again, how the heck does this plasma gets so energized that it can break away from a giant body like the sun and move out supersonically into space and bathe all of the planets? So mystery number 2 on the next slide is, why does this solar wind, how is it continually accelerated? It isn't just a quick burst and then it slows down like you'd pump the gas on the car. You have to keep putting energy in. We would expect this solar wind to get so much slower very going if we just had regular physics going on. So there must be exciting physics going on. And so with the next slide, we're going to go study that exciting physics. And this particular mission, Parker Solar Probe, was first kind of thought of or first proposed in 1958. It corresponded with a little paper written by Gene Parker that really predicted the solar wind and came up with a mechanism for why it would happen. And since 1958, we have been struggling to be able to make our dreams become a reality. Next slide, please. And so why has it taken us so long? And there's no children present, but no one ever knows what this is anymore. This is a rotary dial telephone, kids. And that's what we used in 1958. And if you wanted to make a mobile phone, you needed a really long cord on the phone, so you might be able to walk away a little bit. Now, today, we all have an iPhone X or close, where we probably use that phone for everything except for making a phone call. And that's the kind of leap in technology that it has taken for us to be able to fly a mission to really boldly go where no other spacecraft has gone before. Next slide. So the science of Solar Probe. So the key thing is we are going to go right into this coronal region, right into this 3 million degree region of the corona. Why? Because that is the birthplace of the solar wind. That is where the solar wind goes from being constrained and kind of rotating with the sun. Everybody knows the sun rotates. Everybody knows the sun's got a giant magnetic field. And that magnetic field is so big that it actually constrains the plasma onto those fields. But suddenly, in this region where magic happens, the plasma is so energized that it can break away from the sun, move out, become the solar wind, and carry that really important magnetic field with it that Elsa had just talked about, all the impacts of when it hits our planet. So we have to go in there. We want to discover the source of the solar wind, why it's accelerated, why the corona is so hot, and why you see these incredible energetic particles that you see associated with shocks and with flares and these big coronal mass ejections. And so that's what Solar Probe's going to do. We will launch, and we're very excited. Can you tell I'm excited? We're very excited. We are launching next year. Our launch window opens July 31st. We have a 20-day launch window. The reason for that is we are using Venus to be able to let us go closer and closer to the sun. So it's basically like a planetary launch window. We launch from Kennedy, and we launch on a gigantic Delta IV Heavy with an upper stage. We're a tiny little spacecraft. We look like a little hood ornament on the top of the Delta IV Heavy. Next slide, please. So here is our trajectory. We've lifted off. We come out of the fairing, and we are moving at a blistering speed. We lift off from the Delta IV Heavy, and then you'll see that we have our upper stage, which gives us our final kick. We lift off from our upper stage, and we are on our way to Venus. The first thing you'll see is our solar panels will come out, so we actually are generating power. There's our fantastic heat shield there. Out the back comes the magnetometer boom, where we have our sensitive magnetic field instruments. The next thing you'll see are our electric field. There they come out. And just 6 weeks after launch, we will encounter the planet Venus for the first time. We use Venus, we're very generous. We don't use it, we don't take energy from the planet, we give energy to the planet. We actually use Venus to slow down and trim our trajectory just enough that we can really focus and target the spacecraft to make her first flyby through the corona just 6 weeks after leaving Venus. So in 3 months, we've got a lot of work, busy science team, to get that spacecraft in. You'll notice as we come close to the sun, the solar panels tuck themselves away so that they don't overheat. And there we are coming into our first closest approach. Next slide, please. Just a quick look at the instruments. This one I like to call the bravest little instrument. This one does not hide behind the heat shield. It sticks out in the full solar environment, and it has to deal with temperatures of about 1400, 1700 degrees Celsius. So that's our solar probe cup. It takes It takes measurements of all of the solar wind plasma coming directly towards the spacecraft. You'll see here, I'll talk about this one in a minute. It's got a sister instrument on the other side. It is also part of the sweep, looking at solar wind electrons, alphas, protons, and ions. If we flip over the spacecraft, please, we will see her sister instrument down here, SPAN A+, Justin Casper's the PI, and by having those two instruments on either side of the spacecraft, it allows us to have a full 360-degree field of view of the particle population. Quickly, the WHISPER instrument is a white light imager, taking gorgeous images, not of the sun, but of the solar wind. It's a very unique instrument. It's going to be looking at structures in the solar wind. Here's the magnetometer boom. You saw that in the movie. 3 magnetometers, 2 flux gates, a search coil. Why so many? The magnetic field is really, really dynamic, and we need to cover a huge frequency range. Up here, the electric field antennas, they all together form the field suite. Stuart Bale is the PI. And last but certainly not least, the ESIS suite, taking measurements of the very high energy particles associated with the flares, the coronal mass ejections, the shocks, all the kind of cool transients in the solar wind. Next slide, please. And so I'm not competitive, but we are cooler, we are faster, we are hotter, we are closer than anything has ever been to the sun. We are faster, we are moving at a blistering 430,000 miles an hour, or 118 miles a second. The object of the game is keeping our heat shield between us and the sun at all times, whilst going at that dizzying speed. We are hotter. I mentioned we're going to be right in that coronal region. Our heat shield has to deal with temperatures of 1400 degrees Celsius, 2500 degrees Fahrenheit on the front side. The instruments at the back, they're at room temperature. And I'll go to closer with the next slide, please, because I love this animation. If I put the Earth and the Sun on either side of a football field, and then we'll place some objects so you can orient yourself. Mercury would be at the Sun's 35-yard line. Venus would be back at the Earth's 28-yard line. We have some of the longest coronal loops, can extend out to the 15-yard line here. Now, right now, Helios 2 is the spacecraft that has gone closest to the Sun, and it will make a good rushing attempt and get to the Sun's 29-yard line. Now introducing to the main event, Parker Solar Probe, the newest mission to study the Sun, and she is going all the way to the 4-yard line in the red zone, knocking on the door for the touchdown. So I like to do this because when I say we're going within 4 million miles, people go, well, that's not that close. But that's how close we are. It is that close. Next slide, please. And so I will finish with a look at kind of what's going on. This is the exciting time for me. We're building, we're testing. So here are some highlights from our integration and test. This is from a little while ago. This is when we built the structure. You can see how small that spacecraft is. Here you see us dropping in the harness, and you can see the propulsion tank. So the inside of that tiny spacecraft is really, really crowded. This is when she started to look like Solar Probe. We put the top deck, which really holds our thermal protection system and also keeps up the radiators for how we actually get rid of heat from the spacecraft. There's our high gain antenna on, very important for getting our data back. The most terrifying thing I've ever seen, they hang it by a wire and they swing it. And that is our magnetic swing test, so we can fully characterize all the magnetic fields that are going on in the spacecraft. Here go the solar panels. They're very unique. They are cooled with water. They're in an actively cooled system. I really, really would not want that poor girl's job, but here we are doing the final bonding of the heat shield. This is our flight heat shield, getting ready, dropping it in, and here they are doing the very final bonding down of the top to the rest of the heat shield. And here we are lowering the flight heat shield onto the spacecraft, and that happened so we could do all of the mass properties at APL. We did a full vibe of the spacecraft. It's actually now at Goddard. It's been through acoustic. It has been through it. We've done some testing on the solar cells. And next stop for us, the actual heat shield itself was lifted and put into the big thermal vac chamber just last week. And the next big thing for us is December 26th. We lift the whole spacecraft and we put it into thermal vac. And so the team is excited. With the next slide, please. So just to kind of finish, how many people saw the eclipse? Yeah, awesome, wasn't it? So I just wanted to kind of put into context that, you know, we've really learned everything we know so far about the corona using eclipses, either natural ones or man-made ones with our amazing coronagraphs. But until we can actually fly in and kind of go and knock on the door and sample that plasma in situ, we'll never unlock these questions and we'll never make the true advances in understanding what's going on in the corona. And so, if I put our orbit, you'll actually be able to see the solar probe location during the next eclipse. And I think that's my walk-off slide. So I will just finish by, next slide, thank you, by saying it is almost 60 years since we introduced a solar probe concept. We are delighted that it bears the name for Jean Parker. It was a historic event earlier this year. First time NASA has ever named a mission after somebody during their lifetime. And there is more probability that you will win a Nobel Prize than have a NASA mission named after you. So we are delighted that we carry Jean Parker's name. It is 60 years. We're on our way. Next stop is Cape Kennedy. Thank you very much.